Okay, here we have an example of a rational function. We have x to the fourth plus 1 over x squared. Now, a critical number comes from, it's very important that you remember these three things. The x values where the original function is not continuous. The values of x where the first derivative is equal to 0. And the values of x that make the first derivative undefined. Okay, so restricted values from the original function, restricted values from the derivative, and those values that make the first derivative equal to 0. Well, we know right away that x cannot equal 0. That is a critical number. That is absolutely a critical number. Then we're going to find our first derivative. So f prime of x is equal to, I'm going to rewrite this, f of x equals x squared plus 1 over x squared. And I'm going to find the derivative of it. So it would be 2x minus 2 over x cubed. If I got a common denominator, that would be 2x to the fourth minus 2 all over x cubed. And the book might even go a step further as to saying 2 times the quantity x fourth minus 1 over x cubed. So one of our critical numbers is 0. Now, the next one is going to be coming from setting the first derivative equal to 0. So I'll have 2 times x to the fourth minus 1 equals 0. Because when you have a fraction, it's the numerator equaling 0 that gives you a value of 0. So x to the fourth minus 1 equals 0 means x equals plus or minus 1. These are also critical numbers. So now I have 3 critical numbers. Now I'm also going to get a critical number from the restriction in the denominator of the first derivative. X cannot equal 0. That's a critical number, but it happens to be a critical number that was already stated. So our 3 critical numbers are -1, 0, and +1. So we're going to make a number line, and we're going to test our intervals into the first derivative. Do not forget that we're testing our intervals into the first derivative. So I'm going to use this simple one right here. I'm going to use this to test our intervals. So when I put in a -2, when I put in a value between -infinity to -1, I'm going to get a negative minus a negative. That's not going to help me. I think I need to use, let's undo that. Let's use this, because then we can use factors and I could use multiplication. I don't have to worry about adding and subtracting. If you know anything about me, you know that adding and subtracting is not something that I enjoy doing as much as multiplying and dividing. So multiplying and dividing mathematically is a little bit easier for me to handle. So now 2 is always going to be positive, so I'm going to be looking at x to the fourth minus 1. If I put -2 in, I'm going to get a positive 16. 16 minus 1 is positive, over -2 cubed is negative. A positive over a negative is a negative. That's going to be decreasing. Between 0 and -1, I'll use maybe -1/2. -1/2 to the fourth power is positive 1 over 16. But positive 1 over 16 minus 1 is going to be negative in the numerator. And then -1/2 cubed is negative, so a negative over a negative is a positive. Then I'm going to put a positive 1/2 in. So now we're at the third interval between 0 and 1. If I put positive 1/2 in, I'm going to still get a negative in the numerator, but this time a positive in the denominator. that would be a negative result. If I put a 5 in, 5 to the 4th power is a very big number, 625. Minus 1 is positive. Over 5 cubed is 125, that's positive. A positive over a positive is positive. So our increasing intervals go from -1 to 0 and 1 to infinity, and our decreasing interval goes from -infinity to -1 and then 0 to 1. Okay, we want to show that in the next video, that f of x equals x cubed minus 3x squared plus 3x is increasing on the entire real number line. So on the entire real number line, we already know this because this is a polynomial function. Polynomial functions are smooth and continuous. However, we want to show using calculus that f of x is continuous over the entire real number line. So we want to show that f of x is continuous over all real numbers, So I'm going to find f prime of x, which is 3x squared minus 6x plus 3. I'm going to factor 3, leaving me x squared minus 2x plus 1. And then that's going to factor even further, x minus 1 times x minus 1. So my critical number, also called a critical value, my critical number, sometimes I'll put V, CV, so I'm going to put critical value is equal to 1. That's our critical value. So I've got a number line that only has 2 parts. Okay? So now, what have we got here? So at 1, well, let's go slow. Let's do our math here on our number line. Let's go to, this is the first derivative. I keep saying that because sometimes we forget that we're putting these values into the first derivative. So we're putting them into this value right here. So if I put a 0 in, I love 0. 3 is positive, but 0 minus 1 is negative. 0 minus 1 is negative. A negative times a negative is a positive. Okay, 1 to infinity. Let's put in a 5. 5 minus 1 is positive. 5 minus 1 is positive. A positive times a positive is a positive. If x2 is greater than x1 and f of x2 is greater than f of x1, then the function is increasing. And that's exactly what happened here. Okay? It's exactly what happened here. We're increasing over the entire number line. 1 is not a restricted value. So this is not a restricted value. It did not come from any restrictions in the domain. Therefore, from negative infinity to positive infinity, we are increasing over the entire domain. And that's because the value 1, is not coming from a value that's restricted from the original domain. So that was pretty neato. Now we've got a nifty problem. A national toy distributor determines the cost and revenue models for one of its games. So it's giving us our equations for cost and our equation for revenue, where your x values, your inputs, go from 0 to 6,000. So this model only works for the number of games going from 0 to 6,000. If it produces more than 6,000 games, then not going to work for this model. We want to determine the interval on which the profit is increasing. Well, it's not telling us anything about profit. What is profit equal to? Remember from the previous unit, profit is equal to the amount of money that you take in, which is revenue, minus your cost. So profit is going to equal 7.2x minus 0.001x squared minus all of the cost of 2.4x minus 0.1232x squared. 7.2x minus 2.4x is going to give us, oh boy, 4.8-ish, I believe. 4.8x. So we've got 4.8x. And then minus 0.001x squared plus 0.002x squared. 0.001x squared plus and that's a negative, 0.0002x squared is going to give us negative 0.0008x squared. You can use your calculator if you want, or you can just say 0.0002, 0.001, and then put a 0 behind it. Now we're going to have to subtract. So this is smaller, and that's where your 0.0008 is coming from. And it's negative because this is negative, right? Yeah, good. Or you can just use your calculator. You're good. You're good. You're good because we're doing calculus. Okay, so now we need marginal profit because we want to know where the profit is increasing. So we have to find the first derivative of profit. So that's going to equal 4.8 minus 2 times 8 is 16, right? So 0.0016 x. We're going to set that equal to 0. I don't have any restrictions from my original function or from its derivative. We'll add to both sides, and then it's getting pretty scary here with these decimals. These decimals, I'm not going to kid you. These decimals are frightening to me. 16 over, this would be 10, 100, thousands, 10,000s. Whew, that's a lot of zeros. X, and it wasn't x squared. I don't know why I wrote an x squared right there. It was just x. You're probably wondering, going, when is she going to figure that out? She's never going to figure it out, and then we're going to have to do the video over. Nope, not true. 4.8 is the same thing as 48 over 10. Not true in this circumstance. 48 over 10 times, no times. I'm going to times now though, because I want to solve for x, so I'm going to multiply by the reciprocal. See, this is all me without picking up a calculator, partly because my calculator is in another room. The other part is because this really, we should be able to do this, right? We should be able to do numbers. 48 divided by 16 is 3. 3 times 1,000, that's 3,000. See, it really wasn't that bad. It really wasn't that bad. What did we just do? We found a critical number. Why? Or critical value. Let's use the word value again. Why is this a critical value? Because this is setting the first derivative equal to 0. So we set the first derivative equal to 0. We get our critical value of 3,000, or critical number. We're looking for the interval in which, can't even say negative infinity because it was from 0 to 6,000, right? This is only good between 0 to 6,000 units. So we're looking at the interval from 0 to 3,000. Are we having an increasing profit from 0 to 3,000, or is it 3,000 to 6,000? So let's look at, which one do we want to look at? Let's look at this one right here. Let's look at this right here. if I put 1,000 in, 4.8 minus, if I put 1,000 in, what's that going to do to my decimal place? Well, it's going to move the decimal place over 1, 2, 3 units. So 4.8 minus 1.6, that's positive. Hot dog. Okay, let's see if we're going to have a positive profit, right? If our profit is increasing, not a positive profit, if our profit is increasing, that means with each additional unit, I'm getting more profit than I did from the last unit. Okay, so 3,000 to 6,000. Let's put in a 4,000, right? If we put in a 4,000, 4.8, now I'm starting to get really, I'm going crazy here because I can multiply by 4. 16 times 4 is going to be 64, and then that 1,000 is going to move it over, so that's going to be 6.4. So 4.8 minus 6.4 is a negative number, so that's decreasing. So our profit is decreasing here. We still have a profit, but it's starting to decrease. Over here, our profit is increasing. Therefore, where do we have an increasing profit? We have an increasing profit when selling between 0 and 3,000 units. So that's our increasing profit happens in the interval from 0 to 3,000 units. And that's an example of a word problem, an application problem. This is a perfect example of why brief calculus is required for business majors, because they use it all the time when they're trying to calculate that marginal profit, marginal revenue, marginal cost. The way to do it is through calculus. It's the only way to find that instantaneous rate